Okay, in the part one of section 3.3, we saw how to find the standard deviation and the variance for a set of sample data. We found the standard deviation for a random sample of 8 NCAA football coaches' salaries, and it turned out that the mean salary was about 458,000, and the standard deviation was about $372,000. Well, how do I determine if $372,000 is a large standard deviation? We really haven't talked about what standard deviation means. There are two rules that you can use to interpret a value of a standard deviation. They're called the range rule of thumb and the empirical rule for bell-shaped distribution. The range rule of thumb is based on the principle that for many data sets, the vast majority, such as 95% of sample values, lie within two standard deviations of the mean. Now, let me make sure you understand what that means. Let's say I was talking about a sample of test scores, and the mean of my sample was 80. X bar is mean, and the standard deviation for my set of test scores, sample set of test scores, which is S, is 10. Let's say I was just given that information. If one standard deviation is 10, then what would the value of two standard deviations be? Well, if one standard deviation is 10, two standard deviations would be 20. And what the range rule of thumb is saying is that 95% of test scores would lie within 20 points of the mean. 20 points below the mean would be the mean minus 20 points, or a test score of 60. 20 points above the mean would be the mean plus 20, or a test score of 100. So what the range rule of thumb is telling us is that 95% of all scores would be between 60 and 100. That is what I mean when I say within two standard deviations of the mean. Now, it's time to give an official statistical definition to unusual. So far, we've just kind of relied on our gut instinct. Does this seem like it's unusual? Does it not seem like it's unusual? But in statistics, we have an official definition for what we consider usual and unusual, and it's based on the range rule of thumb. If scores are within two standard deviations of the mean, such as on this previous example, if scores are between 60 and 100, they're going to be considered usual. Not shocking, not surprising. But if scores are outside the range of two standard deviations from the norm, then we're going to consider those scores unusual. We would say it's unusual for someone to have scored a 50 or a 40, but scores between 60 and 100 would be considered usual. We can find the lowest usual value, just like we did on the previous example. We said the mean was 80, one standard deviation is 10, so two standard deviations is 20. The lowest usual value would be the 60 minus two tens. I'm sorry, 80 was the mean. 80 minus two standard deviations is 60. And then find the maximum usual value by adding two standard deviations to the mean. And that's where we came up with the 100. Any scores between 60 and 100 are usual. Any scores less than 60 or greater than 100 would be unusual. So here's an example. The systolic blood pressure of 40 women have a mean of 110.8 milligrams of mercury and a standard deviation of 17.1 milligrams of mercury. Find the range of usual systolic blood pressure readings for this data. First, identify what we're given in the problem. The mean, and this is a sample of 40 women, the mean for this sample of 140 women is 110.8. And the standard deviation for blood pressure of these women is 17.1. We want to find the range of usual systolic blood pressure readings. The lowest usual blood pressure reading would be 110 minus 2 standard deviations. That's 110 minus 34.2, and that's 75.8. I said 0.8 and wrote 0.5. The maximum usual or non-shocking blood pressure would be 110 plus 2 standard deviations. That's 110 plus 34.2, and that's 144.2. So the usual range of blood pressures that we would not be surprised at, blood pressures we would not consider unusual, would be anything between 75.8 and 144.2 millimeters of mercury. That's what we're going to consider usual systolic blood pressure. So, would a woman who had a systolic blood pressure of 181 millimeters of mercury be considered unusual? She's a good bit higher than that 144.2. So, yes, that systolic blood pressure should be considered unusual. She may even need to dial 911 as we speak. There's also a range rule of thumb for estimating a value of the standard deviation. As long as we have all of the data values, we can get an accurate standard deviation on the calculator using the standard deviation function that I showed you. But if we only know the range of the values, we only know the highest and the lowest, then we can't get an accurate standard deviation. The very best we can do is estimate it. And the range rule of thumb says that the best way to estimate the sample standard deviation is just take the range and divide it by 4. Now, range was the highest value minus the lowest value. So do that subtraction, then divide by 4. That is an estimate of the sample standard deviation. Truly, it's not a very good estimate. It's not very accurate, but it's the best thing we can do if we only know the highest and lowest values of our data set. Let's use it to estimate the standard deviation for Rhone State professors' ages. And I made this data up. I don't know that it's accurate. But if Rhone State professors range in age from 26 to 70 and their mean age is 50, estimate the standard deviation of ages of all Rhone State instructors. Here are the keywords: estimate, standard deviation, and I don't know the age of all professors. I only know the lowest age and the highest age, the youngest professor and the oldest professor. So the range rule of thumb says the very best I can do is Find that age range by subtracting 26 from 70 and then divide by 4. The 4 was just in the formula. 70 minus 26 is 44. There's a 44-year age range of Rome State professors. Divide that by 4, and you get that an estimate of the standard deviation for Rome State professors' ages is 11 years. That is not likely to be accurate. It's just the best we can do with the information that we were given. We're also asked within what age range would 95% of all professors be? Well, this is our very best estimate of the standard deviation, 11 years. So 2 standard deviations would be 22 years. And the range rule of thumb says that 95% of professors would be within this 2 standard deviations or 22 years of the mean. The mean was 50. And so 95% of the professors would be between 50 minus 22 and 50 plus 22. That's between 28 years old and 72 years old. 95% of professors would be between 28 and 72. Any professor younger than 28 or older than 72 would be considered unusually young or unusually old. The second rule for interpreting standard deviation is the empirical rule, also known as the 65, 95, 97 rule. But it can only be used when you have approximately bell-shaped data or normally distributed data. If you're not told that your population is normally distributed, you cannot use the empirical rule. If, however, you do know that it's approximately bell-shaped, then these 3 guidelines apply. For data that is normal or bell-shaped, about 68% of values fall within 1 standard deviation of the mean. The second part of the empirical rule just states the same thing the range rule of thumb did. About 95% of all values fall within 2 standard deviations of the mean, and about 99.7% of all values fall within 3 standard deviations of the mean. In other words, if you find someone who is beyond 3 standard deviations below the mean or beyond 3 standard deviations above the mean, that is really, really unusual because 99.7% of all values fall within 3 standard deviations of the mean. Here's an illustration of the empirical rule. If we draw our normal shaped data distribution, and the mean is right here under the highest point. There's our sample mean. Then the first part of the empirical rule says that 68% of the population lies between 1 standard deviation below the mean to 1 standard deviation above the mean. If this was my test score example and I knew that the mean was 80 and the standard deviation was, this time I'm just going to make it 5, so I'm changing the problem, just making up a new problem. If my standard deviation was 5 points, then 1 standard deviation below the mean would be 75 points. 1 standard deviation above the mean would be 85 points. And the empirical rule would tell me that 68% of my scores lie between 75 and 85. The second part of the empirical rule says that 95% lie within 2 standard deviations of the mean. So again, if my test scores mean was 80 and my standard deviation was 5, then 2 standard deviations would be 10, and 95% of all test scores would lie between 10 points below the mean and 10 points above the mean. 95% of the scores would lie between 70 and 90. And then the last part of the empirical rule says that 99.7% of the data lies within 3 standard deviations of the mean. So if the mean is 80 and the standard deviation is 5, then 3 standard deviations would be 15, and 99.7% of all the test scores would be between 15 points below the mean, that's 65, and 15 points above the mean, that's 95. Almost everybody, 99.7% of the test scores would be between 65 and 95. Let's use the empirical rule to estimate a percentage of generators that generate between these two specific voltages. This is based on the Generac generator, which produces voltage amounts with a mean of 125 volts. That sounds like the population of all generators, all Generac generators. So rather than using X bar, I'm going to use the population mean of 125, and the population standard deviation, remember that's the Greek letter sigma, is 0.3. If this had said anything about a sample, then I would have used X bar and S, but I'm assuming that's all Generac generators. Use the empirical rule to approximate the percentage of voltage amounts between 124.4 and 125.6. I just need to know how far these are away from the mean. Well, the mean is 125, and so 125 minus 124.4 is 0.6 volts below the mean. This one's 0.6 volts below the mean. This one is 0.6 volts above the mean. How many standard deviations is 0.6 volts? If one standard deviation is 0.3, then how many 0.3s go into 0.6? 0.6 divided by 0.3 is 2. That's 2 standard deviations from the mean. And then looking back at the empirical rule, what percent of the population lies within 2 standard deviations of the mean? The empirical rule says 95% lie within 2 standard deviations of the mean. So 95% of Generac generators have voltage amounts between 124.4 and 125.6. We could do the same thing in the B part. Subtract each of these from the mean, and you find out that this is 0.9 volts below the mean. This is 0.9 volts above the mean. I'm just going to say within 0.9 volts of the mean. And to find out how many standard deviations that is, just divide by the size of one standard deviation. And you find that that's 3 standard deviations from the mean. Using the empirical rule, what percent of the population lies within 3 standard deviations of the mean? 99.7. 99.7% of these generators would produce voltage between 124.1 and 125.9 volts. That could be very important for safety reasons. You don't want it producing way too much voltage. You're liable to blow the thing up. All right, that is the end of section 3.3. I'm going to go on to 3.4 and talk about measures of relative standing. Z-scores can be used to compare sets of data that have different means. Using Z-scores just standardizes the data. The Z-score of a data set is simply, or excuse me, the Z-score of a data value is the number of standard deviations that value is above or below the mean. On the previous slide, when we said that 125.9 is 3 standard deviations above the mean, I didn't tell you at the time, but that means that 125.9 corresponds to a z-score of 3 standard deviations above the mean. 3 standard deviations below the mean is going to correspond to a z-score of -3. Z-scores can be either positive or negative. They're positive for values that are above the mean. They're negative for values that are below the mean. And to find a z-score of a given data value, you just subtract the mean from that data value and then divide by the size of the standard deviation. That's exactly what we did here when we subtracted the mean from 125.6 and said that's 0.6 volts above the mean, and then we divided by the size of a standard deviation and said that's 2 standard deviations of the mean. That corresponds to a z-score of 2. Same thing for a population. You just subtract the population mean from the given x value and divide by the population standard deviation. We're always going to round our z-scores to 2 decimal places, but you don't have to memorize that. That will always be given to you in the homework and on the test. Now, if we defined usual values to be within 2 standard deviations of the mean, then it makes sense that z-scores between -2 and +2 are considered usual or ordinary, not surprising. But z-scores that are less than -2, that's out here more than 2 standard deviations below the mean, that's unusual. And more than 2 standard deviations above the mean is unusual. So we have a second definition of unusual. You could say outside 2 standard deviations of the mean is unusual, or you could say z-scores less than -2 or z-scores greater than +2 indicate unusual values. Philip Seymour Hoffman won the Best Actor Oscar in Capote when he was 38 years old. That's a little bit younger than average. The average Best Actor Oscar winner is 43.8 years, and standard deviation is about 9 years, 8.9 years. That's for the entire population of Oscar-winning Best Actors. So that's a population mean is 43.8 and a population standard deviation of 8.9. What's the difference between Hoffman's age and the mean age? Well, Hoffman was 38 years old when he won the Best Actor Oscar. So that's a difference of 5.8 years. Now, that actually doesn't indicate younger or older. There's just a 5.8-year difference between his age and the average age. How many standard deviations is that? Well, take the 5.8-year difference and divide it by the size of one standard deviation. And 5.8 divided by 8.9 is about, rounded to 2 decimal places, about 0.65. So he's a little more than a half a standard deviation away from the mean. But again, away from the mean doesn't tell whether he's younger than the mean or older than the mean. When you convert his age to a z-score, that's going to tell whether he's older or younger than the mean. The formula for that z-score is the his age, 38, minus the mean age, 43.8, divided by the size of one standard deviation. That's going to be negative 0.65. The only difference in what we did here and what we did here was the order in which we subtracted. And the reason we got a negative z-score is because he was younger than average to be winning the Best Actor Oscar. Below the mean always gives you a negative z-score. Was his age usual or unusual? Our definition of unusual was more than 2 standard deviations from the mean. Is that more than 2 standard deviations from the mean? No, that's not even 1 whole standard deviation from the mean. So he was younger than average by almost 6 years, but not shockingly so. Not very unusual for a 38-year-old to win the Best Actor Oscar. Another example is heights for women soldiers. The U.S. Army requires women's heights to be between 58 inches and 80 inches. Women soldiers have heights with a mean of 63.6 inches. That sounds like a population of all women soldiers have a mean of 63.6 and a standard deviation, that's a population standard deviation, of 2.5. Find the z-score corresponding to the minimum height requirement. Well, to be a woman soldier, you have to be at least 58 inches tall. So what's the z-score for 58 inches? Take the 58 inches, subtract the mean, and divide by the size of one standard deviation. 58 minus 63.6 is negative 5.6. Divide that by 2.5, and you get a z-score of negative 2.24. I was expecting a negative z-score because the minimum height is below the average, and below the average is always a negative z-score. Is the minimum height an unusual height? Is it a z-score less than negative 2 or more than positive 2? Yes, absolutely. You can be a female soldier at 58 inches, but you're shorter than 95% of the other women soldiers because you're out there past 2 standard deviations from the mean. Find the z-score corresponding to the maximum height requirement. The maximum height requirement is 80 inches. 80 minus 63.6 divided by the standard deviation would be 16.4 divided by 2.5. That's a z-score of 6.4. 0.56. That's even more unusual than a z-score of negative 2.24. This is just barely outside 2 standard deviations from the mean. This is 6.5 standard deviations from the mean. An 80-inch tall woman soldier is very, very unusual. Almost 7 standard deviations from the mean. All right. I think I'm going to do this last example and then break and do part 3 of the video in just a minute. I mentioned in the beginning that z-scores are good for comparing data that comes from data sets with different means. It's really hard to compare ACT scores and SAT scores because they have a completely different range of scores. I'm not sure what the range of scores on the SAT are, but I know on the ACT, I think you can make anywhere in between a 1 and a 36. SAT scores are much higher. So we want to compare an SAT score with an ACT score. We can't really compare a 1518 to we can't really compare an 1190 on the SAT to a 16 on the ACT unless we standardize those scores or unless we find the z-scores. So let's find the z-score for 1190 on the SAT. You would take that score, subtract from that the mean SAT score is 1,518, and divide that by the standard deviation for SAT scores, 325. That corresponds to a z-score of approximately negative 1.01. It's a little more than 1 standard deviation below the mean. And again, because 1190 is below the mean, I was expecting a negative z-score. How about a 16 on the ACT? Well, the mean ACT is 21.1. Divide that by the standard deviation on the ACT, which is 4.8, and you get a z-score of negative 1.06. An 1190 on the ACT or a 16 on the ACT, they're both below the mean. They both have negative z-scores. But if you're going to have a negative z-score, which one of those would you prefer to have? Think of them as balances in your checkbook. If you either way, you have a negative balance in your checkbook, but this one you're in the hole $1.01. This one you're in the hole $1.06. Which is better? If you have to be in the hole, you want to be as close to zero as you can get. If you think about those two z-scores on a number line, negative 1.01 is to the right of negative 1.06, and this would be better because it's closer to breaking even. 1190 on the SAT is better because it's a higher score. It's to the right on a number line. All right, we'll take a break and finish up section 3.4 in just a minute.